In the previous 3 lectures, we've been looking at quantum theories of identical particles. And you can sort of think of what we've seen so far as being the tip of an incredibly large iceberg that we're still exploring to this day. The tip that we have a good understanding of now is the theory of identical point particles in 3 spatial dimensions, or higher. But recently, in the past years, we've been learning about the theory of extended particles, the theory of particles which are one-dimensional, string-like, or membrane-like particles. And the mathematical apparatus to study these things is far from completely developed. It falls under the title or the rubric of modular tensor categories, and it's this subject which we won't cover in this course. But I wanted to make you aware, before we move on to the theory of identical point particles in 3 and more spatial dimensions, that this is really not a completed topic, and there is still tremendous amounts of research, current research going on, understanding identical particles, especially extended particles, extended excitations in 2 spatial dimensions, in higher spatial dimensions, and that this theory is very far from complete. What I am going to tell you about is a theory that's I think it's fair to say absolutely complete, and that's the theory of identical particles in 3 and higher spatial dimensions. And this theory falls under another subject very closely related, it being the tip of this iceberg. That's the subject of Fock space and second quantization. So that's what we're going to cover for the next, I guess, 6 to 12 lectures, depending on what depth and what we see and how fast we go. What we have is we have the Hilbert space of a single particle. We've understood that in the first course on quantum mechanics that you encountered. We've learned about single particles in our elementary quantum mechanics course, and the goal for the next lectures is to work out what Hilbert space to assign to a collection of n identical particles, each having the same single particle Hilbert space, H. That's a task with which we will busy ourselves for the next couple of weeks. Work out the Hilbert space for n identical such particles. And this discussion will very much mirror the discussion we had with identical classical particles. We're going to have 2 descriptions. One will be over complete, And then we will try and work out how to get rid of this redundancy in this description to exactly parameterize those degrees of freedom that are relevant for discussing n identical particles. So what do we know? So we know something, right? To get started on this topic, we're going to need to somehow start with a Hilbert space. And there is one Hilbert space that we know relatively well, and that's the Hilbert space of n distinguishable particles. This is an axiom, this is one of the postulates of quantum mechanics, that if you have a system with Hilbert space H, a system with Hilbert space K, and you form the composite system of these two systems, then the Hilbert space of their composite is the tensor product of their Hilbert spaces. And that's exactly what we have here, the situation of n distinguishable particles. We can tell which one is which. They're labeled by some independent numbers and independent classical labels, and we have n of them. Each of them has the local Hilbert space H, so the Hilbert space for n of them is just the tensor product of H n times. So that comes from the postulate of quantum mechanics. We don't need to further go into any details about this. But what are we going to do to take from this Hilbert space and produce the Hilbert space of n indistinguishable particles? We need to do something, right? It's too much, it's too big. There are states in this Hilbert space which morally are the same physical, represent the same physical configuration if these particles are identical. What are we going to do? So we learned something, right? We're going to elaborate on This is the lesson we learned in the first 3 lectures. The lesson is if you have a quantization of a theory of n identical classical particles, then in 3 spatial dimensions or higher, the wave function obeys this relation here, the wave function for the 2 particles of their positions. It obeys this relation when you exchange the positions of the 2 particles. The wave function's either itself or it picks up a minus sign. Now, there's very many more possibilities for what could have happened, but they didn't, especially when the systems have internal degrees of freedom like spin. Those additional possibilities are called parastatistics. We're not going to cover those in this course. We're just going to look at we're going to look at this observation here and implement this at the level of Hilbert spaces up here. We're going to implement the observation that if you exchange 2 particles, you either pick up a phase of +1 or -1. And we're going to work out how to implement that exchange on this Hilbert space here and how to implement the constraint that the wave function receives this phase change. And what that will do in implementing this constraint here is it will cut out a subspace of this big Hilbert space here. So this Hilbert space here is too big, right? There are states in there, there are vectors in that Hilbert space that different vectors that correspond to the same physical configuration. We have to get rid of these extra ones somehow. So the best way to do that is to find the subspace which corresponds exactly to the right configurations. Now this all connects with something in group theory. This whole idea that we can exchange 2 particles and something happens on a Hilbert space gives us a direct connection between this task of working out the correct subspace describing n identical particles and the theory or the representation theory of the symmetric group Sn on n symbols. The symmetric group on n symbols is a perfectly concrete finite mathematical group. Its elements are all possible permutations of the symbols 1 through to n. It has n factorial elements. I'll just say a couple of words now about the symmetric group. Well, observation number 1 about this Sn is that it's a mathematical group. What does this mean? It has an identity element, it has a product operation, and inverses are also in the group. Its actual elements are described concretely as the permutations of the elements 1 through to n of the set 1 through to n. There are n factorial such permutations. And product is composition. In fact, every finite mathematical group is a subgroup of the symmetric group for n large enough. It's kind of pretty interesting observation. Another nice thing about the symmetric group is one of the few mathematical groups whose representation theory is completely understood. So we have a complete way of constructing all the representations of this group. We don't need this very beautiful and intricate theory, we just need two simple representations. So I'll get to that in a minute. Now, I am assuming you know what I mean by the word representation. Who here understands what I mean by the representation of a group? All right, okay. I better say then what is a representation of a group. There's actually multiple ways of defining the word representation in the infinite dimensional case. Everything's going to be finite dimensional here, so it's not so important, those distinctions. For us, a representation of a group G is just a map it takes for every element of the group. It's a map from the group into some set of operators on a Hilbert space, which just means matrices when H is finite dimensional. And it's not just any map, it's a homomorphism, meaning that if you have two elements of your group, G1 times by G2, then the representation of these two elements, the matrix that is meant to do what these elements do, has to obey this relation for all G1 and G2. And we want that the identity of the group is represented as the identity operator on our Hilbert space. So that's what we mean by representation. So a mathematical group is just an abstract bunch of things. That's not much use if you want to put it on a computer. The best way to put it on a computer is to somehow assign numbers, lists of numbers to each of these things. And a natural way to do that is to find matrices which behave just like the elements of the group. So U of G1, G2 is a matrix, right? It's an element of B of H. And if that matrix obeys this property here, then it's, for all practical purposes, behaving like elements of the group. Now it turns out there's multiple possible such representations. And for the symmetric group, there's really a lot. But we only need two very simple ones. Later on in this course, we're going to encounter another group, the Poincaré group. Another very interesting abstract group. And we're also going to find representations of this group. We're going to, corresponding to every element of the Poincaré group, we're going to find an operator. It will be an infinite dimensional operator, which implements, or which obeys this relation here. Now, our focus in this course will be on unitary representations because we're working with quantum mechanics. These groups will be groups of symmetries in quantum mechanics, groups of operations which leave the physics invariant, and we know that corresponding, and we're going to prove this theorem later on in the course, corresponding to every symmetry operation, there is a unitary operator on your Hilbert space that implements that symmetry. That operator is actually a representation of a group. And although this definition here doesn't make it clear, we can have representations which are not unitary in this sense. But we're going to focus on unitary representations. So there's this additional constraint. All right, back to the task at hand. Here's the core observation on which we build everything. There is a natural unitary action of the symmetric group on H tensor n. It's really what you think it is. I take particles 1 through to n and I permute them around, and that's the action of Sn on H tensor n. So I'll write it out now. I think I'll use a U here. Yes. So let pi be a permutation. So that takes the numbers 1 through to n and moves them around to another list of numbers, 1 through to n. Then the action of u of pi on a vector in our Hilbert space, there's a very natural one we could write down. And it works like this. You just take some vector of this form here. This vector is in this Hilbert space. And you define pretty much as simple as it could be. This pi to the minus 1, I'm doing the inverse transformation there. That's because we're thinking of this operation as a passive transformation rather than an active transformation. It's completely arbitrary. You don't have to put the minus 1 here if you don't want to. And this is for all pi, for all permutations in Sn. So it really does what you think it does. Given a permutation of the elements 1 through to n, how about I do just one example? I like to draw permutations as bipartite graphs like this. So here's the elements 1, 2, and 3. We're talking about 3 elements here. S3 and 3 particles. And I want to take an element from S3, and there's a nice way to draw elements of the symmetric group. You just draw a pairing of the numbers 1 to n with the numbers 1 to n. So here's an example element of S3. This element takes the number 1 and moves it to 3. It takes the number 2, and, sorry, it takes the number 1 and moves it to 2. It takes the number 2 and moves it to 3, and it takes the number 3 and moves it to 1. The inverse, which is what we actually need to do this action here, is also fairly easy to work out. You just flip this diagram around. So what goes to, so the inverse of 2, you have to work out what went to 2. Well, 1 went to 2. So the inverse of 2 is 1. Is 1. The inverse of 3 is 2, of course, and yep, it works out. So if I multiply these two elements, what's multiplication? Multiplication is when you glue these vertices together, and then you check where these numbers go. So 3 would go to 1. If I multiply pi by pi minus 1, 3 goes to 1, 1 goes to 3. So it will act as the identity when I multiply pi by pi minus 1. So this is pi minus 1 here. And what's the action of u of pi on our Hilbert space? Well, let's just apply this formula here. The action is, well, it's pi minus 1 of 1. Pi minus 1 of 1 is 3. Pi minus 1 of 2 is 1. And there's only 1 left. Pi minus 1 of 3 has to be 2. Okay, with this example, I've set some notation here, which is a pictorial representation for permutations. And we've also done an explicit example of the action of this pi minus 1 on some numbers on these index sets there. So you can check that this is unitary. Oh, what I forgot to say is this is extended by linearity to all of H. So that's a nice little exercise to extend that by linearity and to check that it's well defined. What we're going to do now is actually write down the matrix It's an 8 by 8 matrix. So I'll do it. I'll do a couple of entries of this matrix here. I'm going to write down the matrix representation of pi for a certain example. So we're going to continue this example so that you can see see unambiguously that this is defining a unitary representation of the symmetric group on 3 symbols. So let's continue this example and say that H is the simplest possible Hilbert space that we can imagine in quantum mechanics. The simplest one is obviously C, the complex numbers, but that would be too trivial. C tensor C is just C, so that's very, very trivial. We're not going to do that. Instead, say H is C2. That's the simplest non-trivial Hilbert space in quantum mechanics. And already, it makes life pretty complicated because C2 tensored 3 times is 8-dimensional, right? We have to worry about 8 separate basis vectors. I'm going to write a basis, a so-called computational basis for C2. And I'm going to write out a basis now for the full H tensor 3. Now, I told you there's 8, it's 8-dimensional. I'm going to need to write out 8 vectors. Let's write them out. It's fairly easy to do this exercise. Well, that's a vector in our Hilbert space. That's a vector in our Hilbert space. We're at the Leibniz Universität here. The logo of our university has the numbers in binary, in powers of 2, the first 3. We're not going to count like that. We're going to count slightly differently. But this is so far 2/3 of the logo of the Leibniz Universität. And now, of course, we're going to wreck that pattern by writing that as our next basis vector. All right, there they are. There's the 8 basis vectors of H tensor 3. And with respect to that basis, I'm going to write out the 8 by 8 matrix defined by this equation here. Let's write it out. 8 by 8. How hard can this be? "64 entries we have to worry about. But I know ahead of time that I only have to write down 8 numbers. In fact, you know this as well, right? Because if you look at the action of this unitary operator, and you think about the basis that I just wrote out, every single basis vector just gets permuted to another basis vector, not to a superposition. So of the 8 possible basis vectors, you're going to have 8 possible other basis vectors. So there can only be a 1 in every row and every column of this matrix that I'm about to fill out. So we're going to label the rows and columns by the basis vector in question. That's the labels for the 8 columns, and they're exactly the same for the 8 rows. There they are. And the action of u pi, well, it's got to be a matrix, and we're going to put a 1 when this basis vector gets mapped to that basis vector. That's where we put the... I realize I've been forgetting to put brackets around the pi. So it's u of pi. Well, let's have a look at this first one. 0, 0, 0, what does it get mapped to? Any guesses? The same thing. There's a 1 there. And since it got mapped to 0, 0, 0 and nothing else, there's going to have to be zeros in the entire column here, right? What about 0, 0, 1? Well, it gets mapped. Well, I'll do the other one that's easy, right? That's 1, 1, 1. It gets mapped to itself. And then we have to look at the definition of u of pi to start working out some of the other actions, right? So let's ask, where does 0, 0, 1 go to? Well, 0, 0, 1 gets mapped to 1, 0, 0. So there's a 1 here. There's a zeros. Doesn't get mapped to anything else. What about 0, 1, 0? So 0, 1, 0, we just got to follow where the 1 goes. The 1 gets mapped to there, so it's a 0, 0, 1, which is here. And then we've got to do this guy. We just have to follow where the 0 goes. 0, 1, 1 goes to 1, 0, 1. And we already know where 0, 0, 1 goes because it's... Oh, hang on, do we? No, it's 0, 1, 0. Just about have enough to write out the other two without thinking. No. 1, 0, 1 goes to 1, 1, 0. It's like a giant Sudoku now. We just have to work out where the last 1 goes. Well, there's got to be a 1 in every row and every column. So I don't have to work out anything for this last one. There's only one place it could be, and that's here. All right. We've done it. It's our first unitary representation of an element of the symmetric group. It's got a very characteristic form. And you can learn a lot by staring at this particular matrix in the general theory of representations of symmetric groups. It's an 8 by 8 matrix with a 1 in every row and every column. That's our first observation. Some parts of the matrix breaks up into direct sums of other matrices. So if you focus on this 6 by 6 matrix here. This 6 by 6 matrix is by itself a representation of the symmetric group. This 1 by 1 matrix here is itself a representation of the symmetric group. And this 1 by 1 matrix here is also a representation of the symmetric group. It turns out this 6 by 6 one here breaks up as well into smaller blocks, but with respect to a different basis. And it's that basis that we're going to identify. So although this was a very tedious exercise, I insisted on going through it because we're going to see in the general theory that nothing there will be no new non-trivialities that will occur. We'll always have matrices with ones and zeros, and they will always have block diagonal form, and there will exist certain special bases where they further decompose into blocks. Now, that's only the first of 6 possible elements of the symmetric group of 3 letters. I will hereby give you an exercise. This is not to be handed in, this is just for your own practice. That's your task. There are 6 elements in the group S3. We've just worked out the matrix for one of them. However, there are 5 others. In fact, you can do, if you had just about not have to do any work to finish this exercise. You get a bunch for free. You get the identity element of S3. That's where you do nothing, right? The identity permutation. That's easy. We know what that one is already. That matrix is just the identity matrix. And we get 2 other elements, one other element of S3 for free, namely pi squared. Pi squared is also an element of S3, and its matrix is just this matrix squared, which you could pretty much do just by inspection. So you only have to worry about one other element before you get all the elements of S3, because that other element squared is also easy to work out. So it's not such a difficult exercise after all. So we have this Hilbert space of indistinguishable particles. We have this unitary representation of the symmetric group on these n particles. And we have a clue from our study of identical classical particles and quantizations that under permutations the wave function should change by plus or minus 1. We're going to now follow up on this clue and connect that clue to the representation theory of the symmetric group. Let's start thinking operationally. All right, since our particles are identical, any observation, let me put it another way, since our particles are identical, no experiment could distinguish between the state psi and the state u of pi times psi. Not only relevant, but realizable. Okay, there it is. That's the important observation about identical particles. No experiment can distinguish between them if they're identical. They don't have names. They're not Alice, Bob, Charlie. They are really identical particles. If that's the case, then any observable that's allowed, right? So the observables you're allowed to measure in quantum mechanics are usually chosen from the bounded operators on the Hilbert space, but we're not allowed to distinguish between them. So the only real observables that are actually realizable are ones which commute with permutations. They're the ones that can't tell the difference, right? If I permute, then measure, then that's the same as measuring, then permuting. So all the rest are not realizable per definition. All this discussion in the last 3 lectures led to the conclusion that a special role is played by vectors or wave functions such that when I apply a permutation to these vectors, I get back a plus or a minus. I forget to write the brackets around. Pi's. That's the conclusion of our discussion. It could have been more complicated, right? We could have had all kinds of conclusions from the first 3 lectures. But we learned that when you move identical particles around, then the space of wave functions that is of natural quantizations of this action are those that only pick up a plus or a minus sign under that permutation. And yes, I'm going to rewrite this. This may seem like a slightly Baroque thing to do, but it'll make sense in the coming minutes. Another way of saying that u of pi on psi is plus or minus psi is to say the slightly perplexing make this slightly perplexing statement that u of pi on psi is equal to little u of pi. This is my little u here, not my big U, but my little one. On psi, where little u of pi is just a complex number. I mean, like, well, yeah, that's true, right? Plus or minus 1 is a complex number. So it seems like an odd thing to do. But we'll see that this is, in fact, one and the same thing as we get through the next couple of boards. And the first thing I want you to think about as you look at that equation is it looks mightily like an eigenvalue, eigenvector equation. We're looking for subspaces of h tens of n, which are simultaneous eigenvectors of all the permutations. And while that may sound like a completely different thing to the case where u of pi on psi is plus or minus 1, we'll see that in fact these are the same thing. Prove a nice little result now. So a vector which obeys this equation for all pi, there's a lot of equations there, right? There's n factorial equations we have to worry about for this to be true. And this is a vector in a Hilbert space of dimension n to the power, or whatever h is, to the power n. So we're balancing constraints and unknowns, and we'll see what comes out at the end. Now, the first thing we're going to argue is that this little u of pi is a representation. Observation number one, if you permute, then that's the same as just doing the two permutations, the product of the two permutations. But that's an equation. The only way this can be true is if this number, this complex number here, is itself a one-dimensional representation of the symmetric group. We've just learned that this little number u of pi is a one-dimensional representation of the symmetric group. It takes an element of the symmetric group and it produces a bounded operator on the complex numbers, which is otherwise known as a complex number. And it obeys the property that u of pi 1 times u of pi 2 is u of pi 1 times pi 2. So it's a representation. And it's one-dimensional. Okay, how hard can they be? Well, it turns out one-dimensional representations can be kind of tricky sometimes, but for the symmetric group, we can control it. So there are other examples of mathematical groups where one-dimensional representations are much more rich, and one of them is, for example, the integers. So the integers is a mathematical group under addition. The representations, the one-dimensional representations of the integers are phases, and the change of basis from a computational type basis to this other basis that diagonalizes the action is otherwise known as a Fourier transform. So there's a deep connection between one-dimensional representations of groups and the Fourier transform. We won't be able to explore that here because we won't need it because it's very simple in our case. Okay, claim. Now, there might be very many one-dimensional representations. If you know about the integers and Fourier series, then you know that there's a lot, right? There's a continuum of these guys. There's one for every phase on the circle. So there might be really lots of these one-dimensional representations. Well, the claim we're about to prove, this theorem, is that there's only two distinct one-dimensional representations. That's the claim. There are exactly two. So the proof falls into two pieces. The first is going to be left as an exercise effectively, and the second is straightforward. So notes. Firstly, I use tau's and not sigmas. Makes more sense. Okay, fact. Right. This is one you can prove. It's going to be a little exercise for you. Every element of the symmetric group can be written as a product of transpositions. Transpositions just flip to exchange two of the numbers from 1 to n and leave the rest alone. That's an exercise. It's constructive exercise, or it's non-constructive. You can solve it however you want. One way you can solve it is by induction, if you like that kind of thing. Another way you can solve it is by writing an algorithm which produces this sequence of transpositions and showing that the algorithm is correct, converges. Maybe you even find some non-constructive way of proving it, I don't know. Or maybe you prove it by contradiction. I can't imagine how that goes, but I'm not saying it's impossible. All right, so this being the case, that every permutation is a product of transpositions, then we can use a property of little u of pi to deduce that little u of pi is a product of little u of transpositions. Okay, that's just the property of being a representation. But that tells us that all one-dimensional representations are specified once we know what little u of tau is for all j and k. right? If I know little u of tau for every j and k, j not equal to k, then I can work out little u of pi for all pi. So I have to worry about a list now, a finite list of roughly n squared numbers, of n squared complex numbers. But it gets better. It gets much better. If we pre and post multiply by a permutation, not necessarily the same one as this one, then we can use the representation property of u. But this is the same as tau, I think it's pi minus 1 of j, pi minus 1 of k. Let me check that. Yeah, I think that's correct. Although I have something else written in my notes. Ah, yeah, right. There's no minus ones. So this cuts things down considerably, right? Because if I know u of tau jk for some jk, all I have to do is find another pi, and I instantly know that that's equal to this. Because why? I missed out on mentioning an important fact, right? And that is that u of pi is a complex number, u of pi minus 1 is a complex number, but by the representation property, that's just the identity, but that, by definition, is the number 1. So I've just inserted the number 1, and I've learned that u of tau jk is the same as u of tau pi j pi k for all pi. Not just one pi, but all of them. And the proof is almost done. Turns out that for every pair, and this is really easy to convince yourself of, right? For every pair jk, there exists a permutation in Sn such that u of pi j of tau pi j pi k is the same as u of, well, right, it's even easier, right? You can always map j to 1 and k to 2 with some permutation. Hence, these n squared numbers that we're worried about is in fact just one number, because they're all the same number. You just have to say what u of tau 1, 2 is, and then you've specified everything. And what's u of tau 1, 2? Well, we know something about u of tau 1, 2, right? So u of tau 1, 2 squared if you square u of tau 1, 2, you get 1. Because tau 1, 2 is its own inverse. Tau 1, 2 just swaps 1 and 2. And what possible solutions do we have to this equation? Well, there's only two. Namely, plus and minus 1. So we began with the task of working out all the one-dimensional representations of Sn, and that seemed like there could be a lot of them. Then we boiled it down to n squared numbers. Then we used some more facts, and we boiled it down to just two numbers. In fact, we've just proved that there are only two inequivalent one-dimensional representations of the symmetric group Sn, and they're characterized by the property that u of a permutation is a number, and that number is either 1 or minus 1, right? But that's precisely matches with our deduction from the first three lectures that under exchange of particles, the wave function should change either by 1 all the time or by minus 1 if it's a transposition. So this exactly matches that observation. I'm going to distinguish between these two possibilities. One's going to be called the trivial representation, and the other one's going to be called the anti-symmetric representation. So if u of tau 1, 2 is 1, this is called the trivial rep. Why? Because u of pi is 1 for all pi. This one's slightly more complicated. U of tau 1, 2, if it's minus 1, call this the anti-symmetric rep. Case 1, u of tau 1 is 1. That means u of pi for all pi is 1. It's called the trivial representation. The only other case is where u of tau 1, 2 is minus 1. In this case, u of pi is plus 1 or minus 1 depending on the number of transpositions in the permutation. We often have, this guy's got lots of different notations. SGN of pi is one that you may have seen. Another one is epsilon of pi. You've possibly seen things written that way. And what we're going to do is use these two cases to isolate two different subspaces of our n-particle Hilbert space. And they're our candidates for the subspaces describing only the degrees of freedom required to fully specify a system of identical particles. So from here on in, there's going to be a case distinction in everything we do. Either we're doing the trivial case or we're doing the anti-symmetric case. Sometimes we can use a notation which unifies both of these cases. You can just about get away with it, covering both cases at once by introducing the following fancy notation. So write S of pi to be 1 This will get us a long way, this notation. We'll be able to do both cases at once using exactly that. I'm going to start by not using this compactified notation to begin with, just to make it clear the case distinction. And then as we go on, it'll get easier and easier just to employ this notation here. But for the moment, I'm going to do things a bit slowly. We're going to construct now some subspaces of our n-particle Hilbert space. So these are meant to correspond to the identical particles subspace in the case where u of tau is 1 or u of tau is minus 1. Very interesting equations, these ones. So let's just look at these equations, see what they are as objects. Well, the right-hand side is a sum of unitary matrices weighted by 1 over n factorial. Same down here, except we got this plus or minus 1 number here. Now, I'm conflicted whether or not to prove this or to leave it as an exercise, because you can learn really a lot just by thinking through this exercise. Turns out these matrices, they're they're huge matrices, right? It turns out that they're projections. That if I square them, I get them back again. So it's not clear that they're even Hermitian. They are, but it's not clear. So I've written claim prove. this. What I'll do is, I guess I'll give you, like I'll walk through half of the proof and then I leave just critical bits to you. So I'll just do the plus case. How about that? This is really a remarkable thing, right? You take some matrices, you sum them up, and you get a projection. That like almost never happens. So there's something very special about this expression. It turns out this is the basis for all representations of the symmetric group, when you replace this thing here by other characters of the symmetric group. So if you want to get into the representation theory of the symmetric group, this is the central object that underlies it. Okay, that's the first line of our proof. There's not many options here, we just have to expand out this bracket. Still not many options. You know, where do we go from here? We know something, right? We know that u of pi times u of pi prime is u of pi times pi prime. Still more or less forced to the next line. There's not much we can do. We can't get rid of that. Looking at this alone, we can't get rid of it. We have to use some information here. And in fact, there's a trick. This is the only trick in this entire proof. We're going to define a new variable to sum over. And that variable is going to have a name. We're going to call it, let's call it sigma. Right? Let sigma be pi times pi prime. And then the sum over pi and pi prime becomes the sum over sigma. And we got to get from sigma, we got to get pi and pi prime again. So pi inverse, that'll do it. Right? These are elements of the symmetric group. Knowing sigma and pi inverse, I can work out pi and pi prime. So that's as good a way of summing over things as any other. But here it gets interesting, right? Because we've got two sums. We've got a sum over sigma in the symmetric group and a sum over pi inverse in the symmetric group. One of these sums breaks away from the other. And how many elements are there in the symmetric group? N factorial, right? So that cancels out one of these factors of n factorial, and then poof, we're done. Relabeling the dummy index like that. So your task is, of course, to do the other one, but I guess it's fairly clear where that proof is going to go. Now, if you look at these P's and you think about what a projection means, a projection can be associated to a subspace. Every time you have a projection, there's an associated subspace. Let's give these subspaces names. we're going to define two subspaces, the plus h plus n and h minus n. It's just the subspace you get by applying these projections to h tensor n. And that, I claim, these are the two subspaces we wanted to find. And to prove that to you, I'll just do let's just confirm now that a vector from h minus n is anti-symmetric in the way we want it to be, namely that when you permute things, you get minus by psi. Let's just check that. Let's just permute particles 1 and 2 of this vector psi and see what we get out. Well, to be in h minus, n's here, we're going to use this formula up here again. So I'm just multiplying by 1 here. So if you have a state in a subspace and you apply a projection on that state, then you just get the state back, right? So it's just the number 1. Okay, so what happens when I apply tau 1, 2 to it? I can just immediately use this representation property to put them together like this. Let's change variables again, right? Pi prime, and this is just shifts the tau 1, 2 into the sign. But this is a one-dimensional representation, so we can turn it into a product. And in fact, that's just minus 1 times by psi. So flipping 1 and 2 gives us a minus 1, and you can check that flipping any pair gives you a minus 1 in this subspace. Right. We give states in the symmetric subspace a name, we call them bosons. And we give these vectors a name, we call them fermions. These are two subspaces of a very large Hilbert space, and they hardly intersect, these two spaces, and they have very different properties. So if this is Hilbert space here, this is like h minus n here, some subset of our big Hilbert space. These subspaces do intersect, right? There are vectors in common. But that's more than that we cannot say. In fact, they're hugely different properties. One, as n gets large, we're going to see some dramatically different properties for these two subspaces. This one, for example, will grow without bound as n grows, the dimension of h plus n. Whereas this subspace, h minus n, is always bounded. But these are all facts we're going to learn in the coming lectures. This seems like a good moment to stop, so I thank you very much for your attention.